Hello everyone, it's a pleasure to welcome you all once again to MSB lecture series on interpretive spectroscopy. In my previous lecture, I started showing you mass spectra of organic molecules. So let us begin looking into more such examples in this lecture. As I mentioned, let me show you some representative and important and also simple one to understand mass spectra of various molecules having different type of functionalities. So let us first consider saturated hydrocarbons. Mass spectra of linear hydrocarbons display molecular ion peaks which provide the molecular weight. So MCH3 peak, the first methyl group is always weak, and due to the detachment of CH2, fragments will be 14 mass units apart. That means when the fragmentation is there, you can see regular degradation with a loss of 14 mass units due to the detachment of methylene fragments here. So one such example is N-hexadecane is there, molecular weight 226. The parent ion peak is here, and then we can start here. 16 is not shown. The 14 one means probably you have lost 2 CH2 units, and it continues, and you can see up to C2 is there. Of course, saturated hydrocarbons and linear saturated hydrocarbons, it is quite very simple to analyze and understand, and parent peak can be readily identified. So now let us look into some acyclic saturated hydrocarbons. For example, one such, again this is for C6H14, this is for hexane, normal hexane, 86 is there, you can see here, and then this one is losing, becoming C5H11, one CH3 fragment is lost here, and then again if you see here 58 is there, this is for C4H9 plus, and this is 57, and 58 is also given here, you can just look into it, and then we have 43, 41, 42, 39, and also we have 27. So that means very nicely you can distinguish all these fragments and you can give the right mass for them, and then if you make yourself familiar with interpretation in this fashion, it becomes very easy when you are going for unknown samples. So then here you can see all of them I have listed here, starting from this is the one, after losing one methyl group 71, and then it is 58, and then 57 is there, and then we have 56, 55, and then 43, 42, 41. So that means up to 27 you can see a large number of fragments here. But nevertheless, it is very easy to interpret here. And now let us look into the mass spectrum of branched saturated hydrocarbons. So this cationic radical is always present in branched saturated hydrocarbons, and branch fragmentation will also be observed as in 5-methyl pentadecane I have shown here. Here CH3, C4H9 and C10H21. Hydrogen loss will give intense CnH2n peaks here. If you look into 5-methyl pentadecane, molecular weight is 226, this is the parent peak, and then once it loses one methyl group it comes here, and when it loses 4 carbon links and it comes here, and then here it is 6, it is 5, 4, 3, that means up to 3, okay, we can see here almost loss of everything except for 3 carbon, we can see the fragments here. So hydrogen loss will give intense CnH2n peaks in case of saturated branched hydrocarbons. Let us look into now saturated cyclic hydrocarbons. The simplest saturated cyclic hydrocarbon we come across is cyclohexane here. Here branches are cleaved. If there are any branches they are cleaved, whereas the increase in the relative stability of molecular ion peaks is also observed. More and more molecular species become stabilized here. So ring when cleaved consists of even number of fragments, for example C2H4, something like that. So now you can see here molecular ion peak is molecular weight is 84, and then we have 56 here, and then 41 here, it is for C3H5. So now let's look into cyclic saturated hydrocarbons. That's the same thing. Cyclohexane is there. A little bit more I have elaborated here, giving the peaks, the corresponding peaks and the explanation here. So M plus is the molecular ion peak with mass to charge ratio 84 due to C6H12 plus here. The small M plus 1 peak at 85 is due to 113 carbon atom in it, that is 13C 12C5H12. So now isotope is coming, that's abundance of 13C is 1.1. Then 13C accounts for 1%. More carbon atoms in the molecule, the greater the probability of observing this 13C M plus 1 peak. So that means if more number of carbon atoms are there, or more abundant ion peaks of cyclohexane, possibility is their observation. Here intensity of M plus 1 is 6.6. So the most abundant ion peaks of cyclohexane is M by Z is 56, and then this goes to C4H8 plus, and also ethylene comes out. The M by Z 56 is base peak, the most abundant and stable ion fragment. That's the reason you can see 100% abundance of this one. It is formed by the elimination of ethene from the molecular ion. The M by Z value of 83, 69, 55 are related to the loss of a mass unit of 14, that is for CH2, from one fragment ion to the next one. You can see here I have listed all of them, mass to charge ratio, and the fragment which is essentially cation has shown from 69 to all the way. That means after one CH3 here, and then we have C4H9, and then we have C4H8, C4H7, C3H7, C3H6, C3H5, C3H3, C2H5, and C2H3. So you can clearly see all these fragments and their corresponding mass very nicely in this beautiful mass spectrum of cyclohexane. Okay, so now let's look into mass spectra of olefins. So allylic cleavage is a possibility in olefins. So the moment you look into the mass spectrum of olefin, you can see the allylic cleavage and also the fragment having allylic mass. The mass spectrum of M beta myrisine, molecular weight is 136, shows clustering of CnH2n plus 1 and CnH2n and also CnH2n minus 1 at intervals of 14 due to the loss of again methylene fragments, for example CH3, C4H9, C10H21, and also hydrogen loss. When hydrogen loss is there, it will give intense peak of molecular mass CnH2n. So now you can see here one such example is given for beta myrisine, molecular weight is 136. So when it loses this radical, allylic radical, you can see here it comes to 93 here, C7H9, and then it becomes C5H9. We have mass of 69 and 67, then we get C4H7 and then C3H5 plus. The fragmentation, as I mentioned, so here happens that results, or it can also happen here giving the allylic chain. And other possibility is here, when this happens here, this is allylic you can get here, and in this case you can see mass by charge 67, you can identify here C5H9 here, this is the one. And then what we have is here 93, we have C7, H9 plus. So then here you can see again C5H9 plus. So this is how it fragments. It gives some idea about possibility of thinking the way in which the compound can cleave and form different fragments in an unknown sample. This gives lot of information and experience to analyze your own spectrum of unknown samples. Okay, now look into aromatic hydrocarbons. So aromatic hydrocarbons show little fragmentation ions but lots of molecular ions due to the loss of H dot, H radical, and also one can also see the loss of H2 as well as CH2 from aromatic compounds, and this is the one most common. If you just look into the mass spectrum given here of naphthalene here, so here molecular weight is 102 here, and we can see loss of CH2 and it continues like this. So this is not 108, this is 128. Yeah, so then loss of will give you 14, 102. You can also see here some fragments and sub-fragments here. Okay. So now let's look into alkyl substituted benzenes which show interesting features in electron impact mass spectra. So methylene group gets into ring and ring expansion takes place to form C7H7 tropylium cation. How that happens? For example, this is the bond vulnerable for cleavage, alpha beta, and then you can get a radical like this and you can get something like this, and then this one gives a tropylium by this one getting inserted to the ring here. So tropylium cation. So mass to charge ratio is 91. And then on the other hand, through this one hydrogen immigration is there, then we get benzelium radical here. You can see the naphthalene spectrum I have shown, 128 here. 128 is the one and 129 is M+1 due to 13C. Here this shows fragment intervals of 14 due to the loss of CH2 units, and aromatic hydrocarbons show little fragmentation I already mentioned, but lots of molecular ions, and then this is common. So this one is a simulated one and the values I have shown here, intensity and also this one M+1. So now let us look into alcohols. Ion peaks tend to be very small in case of alcohols and non-existent for tertiary alcohols. These ion peaks may not be observed in case of tertiary alcohols. Beta cleavage to the OH is common, resulting in peaks such as CH2OH plus 31, MECHOH or Me2COH species, respectively for primary, secondary and tertiary alcohols, CH3OH, Me2CHOH and Me3COH. So here the mass spectrum is given for ethanol here, 46 you can see here, this is the one, and then you can give, it is giving CH2OH and also it is giving C2H5O and also it is giving C2H3 and C2H5 plus C2H2, C2H3O as we have mentioned here. So and then eventually it gives the last one CH3 plus at a 15 value. Okay, so this is how ethanol shows the mass spectrum, and few more spectra I have shown here. This for 1-butanol and also this is for pentanol. So identify the peaks and maybe calculate and then see the difference between the fragments, so that what kind of fragment has come out from here to here and from here to here. Okay, you can examine these things leisurely. Okay, so now M plus is the molecular ion peak in case of ethanol with mass to charge ratio 46 due to C2H6O plus, that is CH3 CH2OH plus. M+1 peak at MZ 47 is due to C13 12C H6O. So that means 113, 112 and H6O. So now we see a peak at 1+1, that is 47. So ethanol has 2 carbon atoms. So on average 1 in 50 will have a 13C carbon atom. The most abundant ion of the molecule under mass spectrometry investigation is usually given an arbitrary abundance value of 100. That's called the base ion peak, and all other abundances are measured against or with respect to the base ion peak. Okay. So now a little bit more information I have given about this ethanol fragmentation. This explains the principal fragmentation of the mass spectrum of ethanol. This may be helpful in analyzing organic molecules spectra, especially taken from either electron impact or chemical ionization. So formation of M by Z equals 43 and 45 ions. The reason peak at M by Z 45 is due to the loss of a H, actually hydrogen radical from the ionized ethanol. The parent molecular ion is C2H6O plus, which gives C2H5O plus and H comes out. And then mass change 46 minus 1 equals 45. So loss of H2 from this ion from the M by Z 43 ion. That means if you consider C2H6O plus, it gives C2H3O plus H2. So then if you consider formation of M by Z equals 31 is formed by scission of CC bond in the parent molecular ion. For example, if you consider again C2H6O plus, it gives CH2OH plus and CH3, and the mass changes from 46 to 15 is 31. So this is the base peak, the most stable fragment, and of course you can go back and look into the spectrum, and then formation of 28 mass by charge ratio 28 is formed by the elimination of water from the parent molecular ion peak. So for example, if you consider CH3CH2OH plus and if you remove water, you get C2H4 plus. This has 28. Mass change is 46 minus 18, 28 is given. This is the systematic analysis of the spectrum. Then one should do for every spectra you look into. So formation of 29 again, 29 means just look into it. CH3CH2OH, that means plus gives C2H5 ethyl radical plus OH. OH is 17, so mass will be 29. So that means mass 29 is due to ethyl cation. And then formation of 27 ion. Here if you just take C2H5 plus and then C2H5OH plus, so this one, so then it gives, removes and gets C2H3 plus, and then OH comes out. So this is for 27. And then formation of M by Z equals 15, ion is formed by scission of CH2OH and CH3. This is for CH3 is this one. So this is how you can completely analyze and give explanation for the every fragment you see in the mass spectrum. So now let us look into phenols. So molecular ions are more abundant compared to aliphatic alcohols. Common fragments lost are CO, that means minus 28, and CHO minus 29. So mass spectra of substituted phenols differ because of fragmentation of substituents. Okay, the fragmentation happens in different ways. For example, if you look into this one here, there are two possibilities are there, and in one CH3 radical can come out and you can generate a species of molecular weight M by Z 107, or it can get one hydrogen radical coming out to form CH3OH and this species with M by Z value of 121. So these two possibilities are there, and a typical example is shown here for this one with molecular weight 122. So this 107 is also shown here, and 104, 121 is here, and then 77 further goes. That is due to eventually the phenyl radical. Let us move on to another example, mass spectra of aliphatic ethers. The simplest one is diethyl ether. So here we are considering 2-ethoxybutane. This is the one with molecular weight 102, and possible cleavage sites are here as well as here, and also hydrogen migration also possible here. For example, its molecular weight is 102. When it loses one methyl radical, it is 87. When it loses ethyl radical, it is 73. When it loses ethoxy radical, it is 57. And then we get this 45-1. So this is the fragmentation pattern here. And cleavage can also happen here to ethoxy group. And these two are important fragments. 87 is shown here, and also 73 is shown here. Okay, so you can see the loss of ethyl would give 73, and loss of a methyl radical would give 87 value. So now let us look into mass spectra of aromatic ethers. Consider para-dimethoxy benzene. So here the possible cleavage is OC. So methyl radical would come out and you can get a cationic radical, and then this can give you cyclopentenium cation here is 65, and then it can also cleave at both sides to release HCHO to give phenyl cation, C6H6 plus radical here. So if the alkyl portion has a longer chain, then the cleavage leads to the formation of olefin via hydrogen migration. So for example, this is the possible site. If you have a longer chain, in that case what happens, ethylene would come out, substituted ethylene, and we get something like this, and eventually this gives this species here. I think this would be enough. Just go back into whatever the spectra I had shown, just look into, once again analyze yourself and see the fragmentation pattern, so that you would be remembering, and also it would be very easy to interpret, as I mentioned, when you look into unknown sample spectra. Until then, so see you in my next lecture and have a good time. Thank you.